Alright, so welcome back to the second video on optics, and we're just going to continue on with this lecture here. And again, we're going to credit Professor Janusz for making this really useful presentation we're working with. Thank you, Professor. And here we're going to review lens aberrations, and I'm just going to review Professor's lecture slides because they're very useful. We're going to talk a little bit about the image prevention with conventional light microscope. And just to get it out of the way, by light I don't mean the opposite of heavy. This is a light microscope in the sense of visible light. Concepts of resolution, what do we mean by resolution, which is really important to understand, and the concept of resolving power of a microscope. So let's get started here. The lens aberrations. And whenever I like to understand the lens aberrations, and again, all this material should be understood in my mind as a preparation for an exam because I don't intend on designing lenses. So I'm just preparing for questions in exams. So if I could actually explain or prepare myself for an open essay question to explain these aberrations, I have a firm understanding. And I would start explaining any aberration with this sentence. Due to imperfections in the lens system, X, Y happens, etc. This is how I would start describing an aberration in an open essay questions. What's also important to understand is that you have keywords. This is how our department scores open essay questions, which is also a good trick to know. As long as you have keywords, you should be able to get scored for your open essay question. So let's get started by going through the different aberrations that we have. I'd like to kickstart with this image right here, which is a source of concern. Don't worry, you don't need to know this. This is just showing you that there are different lenses that are not thin lenses or not simple lenses. They can have depth to them, multiple focal points on the focal axis or the optical axis. Don't worry about this. This is not a very concern. So let's get started. The spherical aberrations. And what's important to understand is that this is the optical axis, if you don't already know. And what you need to understand with the spherical aberration is that the key words here is that rays entering the lens further away from the optical axis are refracted closer. And by saying refracted closer, they meet closer. This should clue you in that there is more than one focal point. And when there's more than one focal point, like so here, you can see there are two focal points. When there's more than one focal point, you will not have a clear image. So explaining this real quick is due to imperfections in the lens system, a spherical aberration may arise where rays that are entering the lens further away from the optical axis are refracted at a closer focal point. Moving on, coma. And when you look at coma, don't really prepare to draw this. I wouldn't really recommend that. That may be quite annoying. But the first thing about coma is that the object is off the optical axis. And what do I mean by that? When I mean object is off the optical axis, is this, if this is my lens, and this is the center of the lens, and this is the optical axis, the object should ideally be here. And this is where we focus it with our eye on our everyday lives. But in physical systems, the focus of the optical axis with the respect to the object may not always be perfect if there's a problem with the system. The focus is going to be off the optical axis. The object is going to be off of that, off of this line here, which is the optical axis. It's pretty important to know that it shouldn't be there. And in a coma, and also in the next aberration called astigmatism, the object is off the optical axis. You can also throw that the beam angle is large, not a must, but it's important to say that the image looks like a comet sail. As shown here, it's kind of smudging. This is what we'd expect in coma aberration. Moving on to astigmatism. And again, when you look at this, it seems a little bit daunting, but actually it isn't. First of all, a key phrase here is that the object is also off the optical axis. Now if you look at this, I'm just going to draw this. What happens here is instead of having a very fully spherical lens that has the same vertical, horizontal and vertical curvatures, what happens is that I have a slightly somewhat of an ellipse where this curvature is not in the same, it's not the same as this curvature. This causes two different focal lengths. This causes two different focal lengths, or rather two different focal points. And when we have two different focal points, or you can view them as infinite focal points between the two focal points, you have a blurry image. So let's just go through this again. Astigmatism, due to imperfection in the lens system. The object is off the optical axis. Vertical and horizontal curvatures are not identical, resulting in a blurry image and more than one focal point. There we go. Now, when we're talking about this spherical focal surface, which basically what this means is that the object is not on a plane; it's in a curved surface, as shown here. This is the curved surface. This is where the object is. I have never seen this aberration asked about, and it wasn't really explained in the presentation. What the professor said is this could occur, and that was pretty much what he said. And when you're looking at this, if you're looking for material online, there's not a lot of material about this. This is basically the culmination of a few different distinct problems within the lens system. So I wouldn't focus on that, but that is just me. Now, aberrations affected. We have one more aberration to discuss. So let's just keep with aberrations. We'll go back to distortions. Chromatic aberration is when light, polychromatic light, enters the lens system and is broken down to its wavelength components, to the different colors. And in a biological sense, it's called dispersion, and in a physical sense, it's called a chromatic aberration. Now, this basically could happen either in a longitudinal or lateral plane, but all that you really need to know is as light enters the system, and once it passes through the system, through the lens system, it is split to its different colors or different wavelengths. Whereas shorter wavelengths or higher frequencies or bluer colors, they're going to be refracted more and meet at a closer focal point. This is the first focal point for the blue color, and the one after it is for the red color. So the more powerful my wavelength is, or rather, the shorter my wavelength is, the more powerful my light is, the closer it is going to be. And it's going to be the same for both longitudinal and for lateral as far as breaking down of the polychromatic light to its respective wavelengths. That's your key statements here. Now these are aberrations. And being that aberrations have different focal points or more or multiple focal points, they affect the sharpness of the image. Whereas when we're talking about distortions, they do not affect the sharpness of the image. You can think of it as taking this image here, sticking a pin in it, and either pushing it in and getting the pin pushing here, or pulling it out and getting the barrel. If you want to see how this looks, the barrel, just Google fisheye lens, and you will see images that look just like this barrel distortion, which is pretty cool. So this is as far as what we have for lens aberrations in this specific presentation. Bear in mind that if you're preparing for an open essay question, which is a worst case scenario, so to speak, these physical aberrations occur due to imperfections in lens systems. They just stick to keywords. Don't write off forever. They don't like reading all that shit. There's really no need for them to just read on ends. Just write object off the optical axis, beam angle is large, and object formation looks like a comet's tail. Done. Okay, let's keep going. And we're going to talk about the image formation in a conventional light microscope. And even though this may look a little daunting, I promise this is actually pretty simple. What we need to know is to have an understanding of image formation, virtual and real image formation. If you don't have that, if you don't have an understanding of real and virtual image formation in simple or thin lenses, just review the last video. Just to recap, a real image is larger and inverted, and a virtual image is also larger and upright. And I want to just clarify upright. By upright, I mean same orientation, same orientation as the object, as the object. Which means that if this is my object, its virtual image is going to be in the same orientation. And that means that if this is my object, the virtual image is going to be in the same orientation. And you'll know what I'm talking about in a second. First of all, it's important to get out of the way that this focal point and this focal point, these two belong to this lens. Very good. And this focal point and this focal point, these two belong to this lens. And it's important because if you remember the image formation in thin or simple lenses, the type of image that we will have relates, or rather is dependent on where the object is with respect to the focal point. So let's start. First of all, we have our object. This is our object in our microscope. And we can see that with respect to the focal point is between the object and the lens. And this would mean that this object here is going to be reflected as in a real image. Again, because this focal point is between the object and the lens, we're going to have a real image. So this object forms a real image here. And this real image is both larger and inverted, just like we said. So now I have a real image here. But wait, we're not done. I have another lens here. So now being that this is my image and it's facing another lens, it now becomes a new object. So this is the object for this lens here. And this object here is between the focal point and the lens, which means which image would it create? It would create a virtual image, not a real image. So this is the object now, and its virtual image is going to be larger and in the same orientation, or larger and you can say upright, although it is not upright in this instance, but is in the same orientation. So let's consider the end image. This is the end image, and this is the initial object. And I'm only saying initial because at some point this object turned into an image, but this image here turned into an object itself. This image here turned into an object itself, projecting a virtual image. So this is our initial object, and this is our end image. And you can see that our end image is virtual, is virtual to this object, but it is inverted, which is good for us because we said that if we want to see in our day-to-day life, and this was covered in the last video, if you want to see images in our day-to-day lives at proper orientation, they need to be reflected on our retina as inverted. So this is good. We see an inverted image, our mind flips it around, and we have an upright image. This is good. So again, just to recap everything, what we have here is an object placed in a specific orientation that causes it to form a real image. This real true image now becomes the object, and its orientation causes it to form a virtual image. And this image, this end image, is considerably larger and inverted. And this is what we have. This is what we need. Perfect. Let's go through this as well, only because this is also in the same slide. This is a way to calculate the magnification of the image. This is really, really simple, and you'd also need this in the labs. All right, so it's good to get it out of the way. I can calculate the magnification of my image by taking the image size and dividing it by the object size. And when you think about it, let's just say this is my image. My image is 3 centimeters, and my object was 1 centimeter. I have a magnification of times 3, which makes sense. It's not too hard. It's not too difficult to understand here. All right, perfect. Let's keep on trucking. And this is the actual guts of the ideas that one need to understand. The concept of resolution, or the resolving power of a microscope. And the greater the resolution, the better the resolving power. These are actually interchangeable. If I have good resolution, I have good resolving power. If I have poor resolution, I have poor resolving power on my microscope. So these two terms essentially mean the same. Resolution denoted by D, and this is the idea here. It's really important to understand that the D is a distance. And what do I mean? Let's just say I have my microscope here, and I have two different points here. And it's important always to have to know that two different points should be resolved as two different points. If I see these two different points in the microscope like one big smudge, it's not good resolution. I need to be able to distinctly know that these are two different points. Now let's just say that my D, my resolution distance, is this distance. Or rather, I'm going to make it a little smaller, this distance right here. Okay, so I can see that my resolution distance is smaller than the distance between these 2 points. That means that I'm going to resolve these 2 points as 2 different points, which is good for me. I resolve them with good resolution. Let's just say that these 2 points are getting closer together, and now they're standing on that same d distance. I'm still going to be able to resolve them as two different images. Look how close together they get. And let's just say that they're so close together that they are closer together than my actual resolution distance. This means that the image I will get, I will not be able to resolve these two. I will see them as one single point. And you can think about it as having a computer screen, that has 1,000 by 700 pixels, and it has better resolution. We know that it has better resolution than the screen that has 600 over 480. I don't remember the actual ratio, but it's better. Why is it better? It has more points that I can resolve. The distance between 2 pixels here is considerably smaller than the distance between 2 pixels here. So in order to understand resolution, I'm going to write it down. It's the distance. It's the distance between 2 points, in which these 2 points can be resolved as separate points. And it's important to understand that the smaller the d is, the smaller this distance is, or rather the smaller this distance is, the better my resolution is going to be. So the smaller the d is, the better my resolution is. Or the smaller the d is, the better my resolving power of the microscope is. So we want a small d, small distance in which I can resolve 2 points as 2 different points. Now look, a little smiling, perfect. All right, and this is brought to us by the AB equation. And I'm going to put a little s here because there are AB equations. There are 2 equations that we could use, and they're both good. They're both acceptable, but just don't mix them around. I'm going to write both of them down here. I know it's confusing, and they have both of these equations in the presentation. First of is 0.61 lambda. This is the wavelength of visible light over n sinus theta, or, and this is how to resolve d. This is how we can figure out d, or maybe lambda over 2n sinus theta. You can think of the 2 here as, you can scratch this and read 0.5 times lambda, which is actually almost the same as saying this. Very good. Okay, so this is one equation, this is the other, and just to show you where it is, where it's pointed out, you can see this is the first equation, n sinus theta, and here on the next one you will see this one, which is with the 2 in the denominator. So which one is okay to use? Both are okay, just don't mix them up. Don't write anything along the lines of 0.1 lambda over 2n sinus da da da. This is no good. Okay, so let's explain these different components. We already know what the wavelength of visible light is. N is the refractive index of our object. And this angle is the half angle between the objective and the lens. And I know this is kind of weird to understand, so I'm just going to help you by drawing this up. Let's just say this is my microscope here. I'm going to draw it a little bigger. This is my microscope here, and this is where my specimen is. I'm going to write to show you 2 different situations. This is my object here. Very good. And I have an angle here. This is my angle. You can have either a narrow angle or a narrow cone or a wider cone. And you can think of it, this is my optical axis right here, going through the middle. This is not really through the middle, but going through the middle. And this angle right here, this angle right here, is this angle, or the half angle between the objective and the lens. You don't really need to learn to know to describe this. It's not super important, just so you know what it is in case they ask you in the lab. And this whole expression here is commonly referred as to NA, or numerical aperture. And this is what they mean by saying NA here. 0.61 lambda over NA, where NA equals this. So this is the numerical aperture. And now we can solve for D. We want to make D ideally as small as possible. That distance between 2 points that can be resolved as 2 temporary points as smaller as possible. So if we want to decrease D, what can we do? Well, first of all, we can either decrease lambda, decrease the wavelength of the light that we're using, or increase this whole numerical aperture in the denominator, either by increasing the reflective index or by broadening that cone that we saw prior, increasing the half angle. So to get a smaller D, or a better, greater resolution, or a better grading resolving power, all I really need is to either decrease the lambda or increase the numerical aperture. And that's quite important to understand. And if you understand this, if you have a firm understanding of what resolution is, what is resolving power, what is this whole numerical aperture thing, then you probably have a really good platform to go and finish off the optical presentation material. So I will see you in the next video.